first of all, what is the max value of the magnitude of the reflection coefficient? If we assume that the real part of these intrinsic impedances are greater than 0, which is true for passive media. Well, all right, so we've got gamma is equal to eta 1 plus eta 2. Sorry, I'm already getting it backwards. Gamma, so we've got gamma is equal to eta 2 minus eta 1 over eta 2 plus eta 1. All right, I'm going to split these up into their real and imaginary parts now. So that means R2 plus jx2 minus R1 plus jx1, R2 plus jx2 plus R1 plus jx1. Now we can find that the minimum value is just if these two intrinsic impedances are equal. That's fine. But what's its maximum value? If we increase any one of these numbers, R2, X2, R1, or X1, it correspondingly increases on the bottom of this fraction. And all of the other numbers, even if we drove, like, let's say R2 to infinity, if we had some sort of, somehow an open circuit, that's not really exactly possible with a medium, but let's say that it was. If we could create a medium that had infinite intrinsic impedance, the reflection coefficient here would just go to 1. It doesn't matter if we chose a particular value for the imaginary part. It doesn't really matter if we had a specific relationship with R1 or R2. If we maximize gamma, the max absolute value of gamma is just 1. So if R2 goes to infinity, we get that gamma equals 1. But there are other ways to get a magnitude of gamma that equals 1. One of them is to let let eta 2 equal 0. If eta 2 goes to 0, well, then we got 0 minus R1 plus jx1 divided by 0 plus R1 plus jx1. And then we're just dividing minus eta 1 by plus eta 1. So gamma there is minus 1. If we allow eta 2 to be purely imaginary, if we let the real part of eta 2 be 0, then we have jx2 minus R1 plus jx1 divided by jx2 plus R1 plus jx1. Now, usually, we have a good dielectric. So x1 is equal to 0. Because usually your plane waves are incident from some medium in which it's easy to generate a plane wave, which is a good dielectric. So if we have no imaginary part on eta 1, we just end up with jx2 minus r1 divided by jx2 plus r1, which is some complex number where on the top, and actually it's negative conjugate on the bottom. You see how that works? Like if we define some complex number a is equal to minus r1 plus jx2, the bottom is just minus a star, because we've got plus r1 plus jx2. So if eta 2 real part equals 0, then gamma, the magnitude of gamma is also 1, but it's got some phase. All right, so knowing that the maximum possible magnitude for gamma is equal to 1, the second thinking question that we have here is, what's the maximum possible value of the magnitude of the transmission coefficient? Transmission coefficient is 1 plus gamma, so if we end up with gamma equals positive 1, then the maximum magnitude for t is 2. Does this break conservation of power? Actually, no. Because remember, the transmission coefficient is the transmitted electric field divided by the incident electric field. So if you end up with a transmitted electric field that is greater than the incident electric field, that's fine. You still won't end up with a transmitted Poynting vector whose magnitude is greater than the incident Poynting vector. Because remember that that is, for a plane wave, et squared over 2 eta 2 divided by ei squared over 2 eta 1. And in fact, from this, you could work out what does that mean the relationship between the magnetic field vectors has to be. So anyway, this ratio between the Poynting vectors will never be greater than 1, even though the electric field ratio can be greater than 1.